I'm here to talk about closed curves and the Jordan curve theorem. Closed curves and non-closed curves you'll catch on to really quickly once we have some pictures, so let's draw some. Here's an example of a closed curve. Here's an example of a closed curve. Here's an example of a closed curve. Notice that each of them, I started and I ended at the same point. In other words, in the parametrization, here's gamma of A, here's gamma of A plus 1 plus 2 plus 1, and then gamma of B ends up being the same. And this is the case for all of them. So that's a closed curve. A non-closed curve might look like this, where here's gamma B and here's gamma A way over there. They're not the same thing. Another example of a non-closed curve might be like this. Another example of a non-closed curve might just be a line segment. Another example of a non-closed curve might be a circle where you don't quite meet up, right? So I don't know. Closed curves are essentially loops. Oh boy, this is ugly, isn't it? Let's try erasing this to make it look a little better. That just confuses everything. Closed curves are essentially loops, and non-closed curves you can think of as like little string things that aren't tied together. So that's roughly the difference between a closed curve and a non-closed curve, right? Just if the endpoints meet up, it's going to be closed. Otherwise, it's going to be not closed. And the Jordan curve theorem says that these closed curves over here, it says two things actually. Well, as far as we're concerned, it says two things. It says that these over here, these have an inside and an outside. And an outside. And this should be intuitively true. Alright, I mean, here for this one, here's the inside. It's this part. Here's the outside. You might think that this is completely obvious, but nothing is obvious to mathematicians, right? We have to prove everything. And in fact, this turned out to be rather difficult to prove, which is why Jordan got his name attached. If it were easy to prove, it'd just be the curve theorem. So he gets a lot of credit for that. Inside, outside, inside, outside. This one, there's no inside and there's no outside. Similar with this, here you almost have one, except the inside leaks out into the outside. So that's one thing that the Jordan curve theorem says. It also says that if you have a loop inside of the curve, so maybe if you have a little thing like that, what it says is that you can homotopically cause it to kind of spread out and turn it into this green curve. So a little loop on the inside of it can be homotopically, in a very smooth way, morphed into this green loop outside. So that's what the Jordan curve theorem says. And those are what closed curves are. Thank you.